Alright, remember here about finding vector. We probably ought to know what we mean by vector components. So we're full-blown vector mathematics here, and ourselves a vector. And it's a displacement vector of 5 meters. And now what we're going to do is we're going to talk about the direction of this, not in terms of just where the arrows point, but in terms of an angle with the horizon. And let's say that this is at a 40-degree angle. So all I've just said that this is 40 degrees kind of north of on the horizontal axis. Now, what we're going to do is we are going to find what are components of this. And it's basically saying, what if I took this vector and made it the result of adding a vector along the x-axis and a vector along the y-axis. So now I'm thinking of this vector as being the sum of this vector and this vector. And I'm saying if I do that, what's the size of this vector and what's the size of this vector? Because now I know their directions. This one's directly north at 90 degrees. This one is at 0 degrees. So now it's just a matter of, can I find the length of these two vectors? And it turns out we can using trigonometry. So there are 3 functions that you're going to have to know very well. There's the sine function, the cosine function, and the tangent function. And what these do is that it's just a function, so you put in some number and it does stuff to that number. We usually call this, in variable terms, we call it theta. And theta represents some angle. So in this case, if we were to take the sine of whatever angle we want, let's say 40 degrees, I would say the sine of 40 is, and then we have ways to compute this. So all of these are functions, and all scientific calculators are going to have that. Now I should say a word about this that I just kind of assumed and maybe shouldn't have, is that all of this that we're about to talk about only works with right triangles. Now the reason I could just assume that was that if we take this vector and we break it down into something that is the sum of a vector along the x-axis and a vector along the y-axis, these automatically have to be 90 degrees of each other. So again, this only works for right triangles. Alright, so let's start with the sine function. The sine function is equal to opposite over hypotenuse. Which you're probably saying, great, how does that help me at all? So here is, I'll put this underneath it so we can break it down. We're basically looking at this as being a right triangle. And if I say that this is my angle theta, I'm breaking down the sides of this triangle into different parts. And so let's start with this. I said this was opposite. So what that means is I look at the angle and I find the side that is directly opposite of that angle. So it's not touching it. In fact, it'll be the only side of the triangle not touching it. This would be called the opposite side. The side that's touching the angle is called the adjacent side. And the other side, the longest side, the side that is across from the 90-degree angle, is called the hypotenuse. So we have the hypotenuse is the one directly across from the 90-degree angle, the longest side. The opposite side is the one that is directly across from the angle, and the adjacent side is the one that's touching it. So the sine of theta is equal to the length of the opposite side divided by the length of the hypotenuse. The cosine function, so cosine of whatever angle is equal to the length of the adjacent side divided by the length of the hypotenuse. And for the tangent function, it's the opposite side divided by the adjacent side. And once we get using these, you'll get used to remembering what these all mean. In the meantime, there's this nice little mnemonic that can help you remember. I think of it as being a Native American name, however you want to do it. But the phrase SOHCAHTOA will take you very, very far in remembering this. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So this is a handy way to memorize all three of these. And in fact, I've been doing this for years, and this is still how I remember what these functions mean. All right, so we know what these functions are. We know how to break this down. We know what all the different sides are. Now we can start using this information to find out what our components are for this vector. So I'm going to recopy this down here just so we have sort of a clean slate to work with. So we have our vector of 5 meters. We have our x component and our y component. And the names come from the x component is the one that runs horizontally along the x-axis. Y component is the one running up and down. And we said our angle was 40 degrees. We don't know the length of this side. We don't know the length of this side. So now let's work on trying to find one of these. And let's start by finding the y component. So I'm going to make a note to myself that I'm finding the y component right here. And notice that the y component is opposite of the angle. So I want to look through my functions and find which ones have the opposite in them. Sine does, tangent does. I don't know the length of the adjacent side, but I do know the length of the hypotenuse. So to find this y component, I'm actually going to use the sine function. And here I say that the sine of 40 is equal to the opposite side, we don't know what that is, divided by the hypotenuse. Well, the length of the hypotenuse is 5. And remember, this y value that we're finding here is the length of this side. And now, it's just a simple matter of solving this problem. If you want to, you can go ahead and figure out what the sine of 40 is. Mathematically, the easier way to do this, let me sneak my calculator into the picture, is to actually multiply by 5 first. Remember, we want to eliminate our fraction. Multiply both sides by 5, and we get 5 times the sine of 40 degrees is equal to y. Now, to put this in a calculator, for this particular calculator, what you want to do to enter in one of these trig functions is you make sure first that you're on degrees and not radians. Radians are just another way of measuring angles. Let's see if I can get my document camera to focus on this. Oh, it's still going to be tricky to see, but there's a little DEG in there that stands for degrees. So we can change this from measuring between degrees and radians. We're going to stick with degrees in this class. So we want that right there. And now all you're going to do is you're going to enter in 40 and then hit the sine function. And this tells you that the sine of 40 is 0.642, so on and so forth. I wanted to take all of that times 5, and so the length of my y component, I'm just going to round off to the hundredths place here. If you've learned sig figs, it's much better to use those, but for now, I can say that the length of the y component of this is going to be 3.21 meters. Bring this back into focus. So I can fill that in now. 3.21 meters. And I can do the same type of work to find the length of the x-axis, or the x component rather. So designate that I'm looking now for the x component. This is the adjacent side, so if I look back through my functions, I am going to want to use the cosine function now to find that. And I say that the cosine of 40 is equal to the adjacent side, which is the x component, divided by 5. Just as before now, multiply both sides by 5, and 5 times the cosine of 40 will give me that value. So I take 5 times the cosine of 40, and I find that the x component of this is 3.83, and this is a length, so it's meters. 3.83 meters. And now I've found, again, my two vectors that if I add them together will give me that right there. Now, let's talk about usefulness of this now that we have the basic idea. The reason this is useful is suppose, for instance, that instead of a distance, this is a speed. 5 meters per second at 40 degrees. Say somebody threw a baseball at an angle of 40 degrees at 5 meters per second. That baseball, if I break this down into components, it's moving in the x direction, left and right, 3.83 meters per second. I found out how fast it's moving in this direction. The y component will tell me how fast it's moving in that direction. And if you think back to what you know of projectile motion, you want to separate the x and y directions. And so now you can take a projectile thrown at any angle and find the x and the y parts of its velocity. And this can be done for any vector, acceleration, force, anything that is a vector quantity is subject to all of this. Now that we have that, we're next going to look at solving some problems that get a little bit more complicated, because now instead of all the velocities being along the x or the y axis, we can play with whatever we'd like.